we don't need this, and then we say make GDB. Nice. So these are then the registers that we were talking about. The APSR is marked as CPSR. I think, what does CPSR stand for? Program status register, I suppose.
CPU program status register. So basically PSR has been marked as
Right.
CPSR.
Oh, it's just the okay, obviously, yes. The PSR, not the APSR. Yeah. What are we going to look at now?
Okay, so in this one, so I guess in the previous one we looked at the Cortex and the ARM introduction to the ARM families and different ARM families that we have, and in this we would go into depth of one of the implementations of the Cortex-M families, that is Cortex-M4. The reason to do that is in future videos we will cover one of the devices that uses Cortex-M4 as its CPU for our different demos, and that will be STM32F4 Discovery, which kind of looks like this.
Nice.
And we'll do multiple experiments on it. So before we jump into using a device that contains Cortex-M4, we will not go into much depth about Cortex-M4. We will not go into the assembly language, etc., all the instructions, etc. I think we'll do a separate. Right now, we'll do a separate playlist where we specifically focus only on the assembly language and different aspects of the CPU itself. And keep the device out of picture. At that point. So in this, we'll just assume that you know the C language and compiler, and you know how to run the compiler to do your job. Okay. So in this specific video, we will cover Cortex-M4's core architecture, the general purpose registers and special registers. Keeping time in mind, we will not discuss exception model. I want to cover it along with the complete programmers model. Of the CPU. So we will just look at the very base of the Cortex-M4.
Right. So only these three.
Only these three.
Now. Right. Perfect. Okay. So then let's move on. What's happening here?
So when we look at the Cortex-M4 is just, and that's the specialty about Cortex-M family. It's just not the CPU, right? It's just not a processor. There are multiple things around it that makes it a complete system. So the Cortex-M4 has a CPU which is based on ARM v7M. And it implements a floating point unit. To be precise, it's a single precision floating point unit. And it is optional to the vendors. If vendors, let's say, don't see their device getting used for any floating point arithmetic, they can choose to disable this. And this variant of the Cortex-M4 is specifically called Cortex-M4F. So this is just to highlight that if in future you read a datasheet and it says instead of Cortex-M4, Cortex-M4F, it's not a separate device. It just means it's Cortex-M4 with FPU enabled.
Right. And FPU
not enabled, capable. FPU capable.
Right. It's available. You can choose to enable it. Yeah. Fair.
So, and if you look on, we look on this left side, we have the interrupt mechanism. And that's where we talked in the last lecture, which differentiates Cortex-M4, Cortex-M families with Cortex-R and Cortex-A's. It has its own vectored interrupt controller inside.
Right. So this is the nested
vector interrupt controller.
Interrupt controller, yes.
And we also have something called a wake-up interrupt controller, which is usually very transparent, not very often, even often used, don't need much programming interface of it. Usually it's like a non-maskable interrupt. And so the point with the wake-up interrupt controller is, so ARM has different sleep states. So when you put the ARM into the lowest sleep mode, the only logic that is active at that time is the wake-up interrupt controller. So it can wake up ARM from the deepest sleep state possible. So usually vendors will connect this wake-up interrupt controller to something like RTC or watchdog timer, etc.
Okay. So the
where you
idea
want the
is that if
lowest sleep
this,
mode.
Mhm.
So this is usually called in typical devices, we call this a backup domain or something. So usually RTCs are
Okay.
the only logic running in the system at that time, keeping track of some
Mhm.
time, and they can bring the device back from such a state.
Okay, so let me just reiterate. What you're suggesting is if this much logic or this
Yeah,
much part is completely asleep, right, in low power state,
yeah.
then this is the only thing that is active.
This is the
And
only
once an
thing that is.
interrupt, right, once an interrupt comes to WIC, it'll go ahead and wake up everything else.
Yes.
Okay, okay, fair. I think that is well understood now. Go ahead. What else?
So except this, we have on the right something called a embedded trace macro cell.
Mm-hmm.
This is again a very optional. So anything that you see in a pinkish shade is optional in the
Okay.
device. So embedded trace macro cell, it is used for tracing. So let's say you want to do an
Mm-hmm.
instruction state. You want to know what was getting executed at what time.
Mm-hmm. Mm-hmm.
So this keeps a real-time hardware level trace of
Right.
what where the CPU spent most of its time, and later on
Mhm,
that data can be analyzed to come up with different analysis. Like you can
mhm,
use it for coverage
mhm.
analysis, whether all the functions were triggered or not. You can
Right,
do it to track which function you spend the most time on.
right, right. So
You
this is
can do
typically
real-time
for,
analysis on it.
right, debug and instrumentation.
Debug and trace. Usually people call it debug and trace.
Okay, fair. And when you
Yeah.
say it's optional in the sense that it's available, it can be enabled if the programmer wants to.
No, it depends on the vendor. So when a
I
vendor
see.
takes a
Okay,
ARM design in, they can choose whether ETM should be part of it or not.
understood. So this is optional at the implementation level.
Yes, at the implementation level.
Okay,
ARM
may
will
not be.
provide it. It's up to vendor whether they want to enable it in their design or not. They want to pick it up or not.
Okay, understood. And this is the same story with FPU or for
FPU,
M4.
same for FPU.
I see. Okay, so the vendor
Vendors
can
can
decide.
choose to completely disable floating point unit.
Understood. Fair, fair. Okay. Okay, then moving
And
on.
then you have something called debug access port. We usually call them DAC ports.
Mm-hmm.
So these are used to interface a debugger with with the ARM CPU. So this is the debug
I
mechanism
see.
for ARM CPUs.
So
And if you want
something
to
like
do
a,
any kind of JTAG SWD, more precisely it is SWD,
okay,
which is the ARM standard.
right, right, right. The
Uh,
serial
Serial
wired,
wire
the
debug.
single, yeah, okay, serial
Serial wire
wired,
debug.
right.
Uh,
Okay, perfect.
and then you have something called memory protection unit.
Mm-hmm.
Memory protection unit is used to segregate memory into different privilege levels. So let's say
Understood.
you want some memory to have a higher privilege level and can only be executed in kernel mode. So specifically when we talk about RTOS kernels and user space, right? So then you
Mm-hmm.
want to segregate the memory as well. You want the kernel space to be having a higher privilege so that CPU can access that place only when it's in a higher privilege state.
Understood. So, well, I'll just maybe add to it that the MPU is essentially a table, right?
Yes,
And then you give like a starting and end address of like the memory region, and then you set some attributes as
yes.
to whether it is just read only, read write, or read write execute, and then something else also, whether handler mode can access
You
or
can
anything.
access privilege levels as well, whether it is handler. You can define privilege levels.
Okay. I don't specifically recall if I ever programmed in the privilege level also, but I
Maybe
think
because
maybe that's
you always your code was monolithic and always run in. There was no kernel separate kernel
mm,
space for it.
right,
There
understood.
was no
And
separate
now,
kernel.
now that we are referring to the kernel and the user space, I think it's worth mentioning that the M class CPUs have something called
Thread
the
mode and
thread
handler mode.
mode and the handler mode. So thread mode has like few of the hardware things disabled, hardware features disabled, privileges not as much, and handler mode has like complete control of the system, so to speak, full access to the system and
Yeah.
instructions. Okay, cool. Anything that we missed on this slide? I think the bottom
Uh,
things here.
and the next part is we have a SysTick in the Cortex-M device, which is basically a
Mhm.
down counting timer,
Yeah, I think it is a 24-bit
24-bit
down.
down counter.
Right,
And
right.
the reason of putting this in place is specifically for RTOS purposes, operating
Mhm.
system purposes, because operating systems need a timer base.
I
So
see.
putting a
Mm.
timer within the core itself makes the operating system port for that core universal
Mhm.
across all the devices. So
Makes
irrespective whether it is STM, microchip, or NXP trying to do a RTOS port on this device, they don't need to do port again. ARM does the port once and it works for everyone. But if
I
this
see.
timer
And
was
then,
not there, but if SysTick was
haha,
not there, then each one has to implement an interface for their
their
timer
own.
counter.
Right, right. And then again to, kind of bring to notice the fact that, the SysTick, memory protection unit, debug access port, NVIC and VIC, they are on specific addresses across all the
Yes.
M4 processors, irrespective of which vendor is implementing them.
Yes.
Okay. So the addresses are also always same. Perfect.
Yeah.
Do we want to talk about the bottom two, three things now? The bus matrix
Uh,
and other
I
things?
have specific slides on it in future covering about the interconnect and the whole concept of memory mapping and what's
Okay,
the role
fair.
bus metrics and all these buses play there.
Okay, okay,
So we will
fair.
cover in much more depth over there.
Hmm.
The
Sure. So let.
so I
Mhm.
would just say the reason. So the bus matrix is just used to separate buses based on the memory map. Let's say you want
I,
to
I
access
see.
something in a specific range, it will go on a
Mhm.
defined bus. If you want to access something on a different bus, different address space, it will go on a different bus. Similarly, like say
Understood.
if you're accessing SysTick, the bus matrix will redirect it to the SysTick within the
Mm.
CPU itself.
Understood. Understood. Fair. I just want to reiterate what you mentioned. So M4 CPU is the V7M, based on V7M architecture, right? So FPU is optional. So is ETM, debug access port, and even MPU. Is that optional?
MPU is optional.
It is. Okay, fair, fair. So MPU is for setting access permissions and privileges. ETM is the trace macro cell. Debug is the single wire debug interface, the ARM standard. For those purposes, NVIC is the nested vector interrupt controller that will deliver interrupts to the CPU. FPU is floating point unit. WIC is the wake on interrupt controller,
Wake up interrupt controller.
wake up interrupt controller. And in low power state, all of this logic will be sleeping or in low power. And if an interrupt comes, certain kind of interrupt comes, then the WIC will catch it and wake up the logic, and then it will be delivered to the CPU. Okay, SysTick is the 24-bit down counter. Memory protection we talked about. What else? This we'll talk about later. Yeah, I think we're good. Should we go to
Yeah.
the next slide?
And we will
Yeah,
cover
okay.
each one of these in details in separate course
Hmm,
for the where we
fair.
focus specifically on Cortex-M CPU itself. We'll learn
Right, fair, fair.
how to program memory protection unit, how to program ETM so that you can take real-time traces out,
Mhm.
how to
Right,
program a
right.
sysdig.
Hmm.
Yeah. Okay.
Perfect. So what we are now doing is we are trying to understand at a high level what this processor is, what the parts are, try and program those, the important bits, and then slowly as we peel the onion, we'll go ahead and program everything.
Yes.
Right.
Yes.
Okay, perfect. Right. Let's move on to the Endianness.
Yeah. So whenever we talk about a CPUs, the common question CPU or any kind of interface, the things that you will often read and talk about is the Endianness of the system, right? How the
Mm-hmm.
data is stored, and sometimes people don't realize it. So I have seen people opening a debugger, looking at a memory view, and realizing that the
Mm-hmm.
numbers are not written in the right,
Right.
saying that the
Not as
data
they
is
expected.
corrupted,
Yeah. 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 Yeah.
and
Yeah. Instead of
thinking that
one,
the
two,
data
three,
is
four,
corrupted.
it's
Yeah,
yeah.
instead of 1 2 3 4, they see 4 3 2 1, and be like, okay, maybe I'm doing something
Corrupt.
wrong.
Right.
But
Right. True.
actually, it has to do with the Indianness of the system, how the system tries to understand the bits. And typically, we
Okay.
have to
Maybe
confirm.
could you speak about. Sure. Could you speak about Endianness itself? What that means?
So Endianess itself means is, so let's say if you have a number like 1, 2, 3, 4, it's about how you place the MSB versus LSB.
Okay, this being the MSB and this
Yes,
being the LSB. Right.
yes.
Okay.
So if
And
you're a
then,
little Indian, the LSB goes first and ends in. Uh,
okay,
isn't you right? Didn't you write it opposite? You are a little Indian minded. Least
am I?
significant bit should be one, and the most significant bit should be four. Byte.
Okay, so for me, the memory is going this way. So I
So it
have
cannot be most
written it
significant,
big.
right?
This is okay. Fair. Okay, let's do nice.
Yeah.
Yeah, the
Yeah.
live confusion. Let's do this.
So just to highlight, I guess so majority of the CPUs out there are little Indian systems, and this is 8 years of experience, which basically starts telling us that this is how
Yeah,
CPU is going to present it.
yeah. So I just want to maybe do it this way: one, two,
Yeah.
three, 4, 5, 6, 7, 8. Yeah, same example.
Yes. Yeah.
So when we represent this in the CPU register, let's say, right, the 32 bits, wouldn't 1, 2 go in the lower byte?
Yes. So that's why it is
Not
least
lower byte,
significant, right?
not lower byte, the highest byte.
No, right?
Okay,
The left
okay.
is you start from left, right? So indexing starts from left. So it is 0, 1, 2, 3, 4. So 0 means the least significant, right?
0 is
Okay,
least
I see
significant.
your point. You're talking
Yeah,
about
the
tens
CPU
in terms of
internal.
tens, right?
Yeah.
Okay, now I am confused.
Okay, so let's talk about adding 1 to 1.
Okay,
So I imagine if this is a 32-bit number,
yes,
both of them, then in the CPU register, the 1 will show up here.
yes,
And
yes,
this
yes,
is the LSB side, and this is the MSB side. So I was thinking in
yes.
that terms. So if we were to add this number to 1, for example, then this must be represented, hopefully, like
One,
so,
two, three, four, five,
right?
6, 7, 8. Yeah,
Right.
so this
Uh,
is what is big Indian, right?
yes, this is Big Indian. That is
This is
correct.
big Indian.
And when I think of Big Indian, I'm like assuming, okay, this is Big Indian, yes, let's not confuse our audience. If this happens to be stored, okay, like so, this would be Big Indian. The
Yes,
MSB is stored in the least address,
yes,
right? And if it was stored, okay, let me see. If this was stored this way, then it's Little Indian.
yes.
The LSB is stored first.
Hmm.
Okay, nice. I suppose, oh, okay, perfect. So we exactly mentioned the same thing. So if on the first address, the lowest address, if you have the lowest byte being this,
Yes,
then you have the Little Indian. If you write it or read it as if you're writing the numerals, the normal Arabic or mathematical
yes,
number, then it's Big Endian. The biggest
yes.
value goes on the uh,
Looks.
lowest address.
So
Perfect.
big Indian
Hopefully,
is the natural one.
yes.
Little Indian, as you gave the example of addition, right? That's the whole reason why people go for little Indians, because little Indian is
Uh-huh.
on the lowest end,
Ah, I
zero.
see.
So
I see.
adding
I
that,
see.
so when you want to, so the amazing part is, okay, let's say if this is the value 7856, this is the variable, and I want to access 8 byte, 16 byte, or
Hmm.
32 byte. Sorry,
Hmm.
8
Hmm.
bit, 16 bit, or 32 bit. I don't need to change the base address. I just need to change the width I want to access. The base address
Ah, makes
remains the
sense.
same.
Makes sense. Makes sense. Makes sense. So you're saying if you wanted to access only this much, you could
Yeah.
still point here and then extract this much. But if you
Yes.
needed, let's say, all the 32 bits, you could still be pointing to 0 and extract
Yes.
all the 32 bits. If it was Big Endian,
You
which
have to
was
change the pointer at the base address.
Right. If it was, this is a good one. So if we wanted to now access 5678, we would first have to come here, then
Yes,
extract
exactly.
two bytes.
So it was
I
much
see.
more
I see.
natural for CPUs to do a
Yes,
little endian,
little Indian. Yeah, I understand
and
that now.
but it was unnatural to humans. That's why most of the big endian you see in most of the protocols are in big endian format. So whatever you see coming out on the lines will always be
Mhm.
big endian, so that it is easy for humans to read.
I see.
While
Okay.
majority of the internal processing will be in little endian.
The other reason for Big Indian that I thought was the case is that, if you, yeah, I think that was a bizarre reason, but let me just put it here. So if you have 1, 2, 3, 4, 5, 6, 7, 8, and you kind of shift them left into another register, for example, right,
Yeah.
assuming if you move it into another buffer from where it was to be transmitted, then the transmitter can, just walk from MSB to LSB
Yes.
and then just send it over. But that was my reasoning. Anyways, I don't know if that is accurate also, but I made peace with that. Okay.
So my
Okay.
understanding was that since it is very natural for us to read numbers in a big endian format,
Mm, mm.
most of the communication protocols use it so that it's easy to
We
debug
can
and it is
debug it.
easy to yeah.
Understood. Understood. Right. Yeah, kind of makes sense, as I think more about it. Let's say if we were transmitting in Little Indian, right? And so we want, let's say if we see 1, 2 first, we wouldn't know if it is part of the packet. So, like the packet header, okay, let me put it this way. So we have 32 bytes, bits, sorry, 32 bits. Yeah, I'm going to confuse people now. But 32 bits. And let's say the upper 1 byte is actually the header. Then we have the data, and then we have more data, right?
Yeah.
And in another 32 bits somewhere we have the. So if we were transmitting in the big Indian, then the
Yes.
header goes out first.
Yes.
Versus if it was little Indian, then this some part of the data goes
Yeah.
out first, and if that
Yes.
is there is an error there, we wouldn't know which packet.
CRC goes out first without telling that the
Yeah,
packet has
yeah,
started transmitting.
makes sense. I think I'm convinced. I hope
Yeah.
the listener or those who are watching. Hopefully, we haven't confused them yet. All right, should we move on then?
Yes.
Okay, let's go. Yeah.
Okay, so this is where things take a different turn when we talk about Cortex-M family. Even though the
Mm-hmm.
Cortex-M family is a 32-bit CPUs, not all
Mm-hmm.
instructions are 32-bit wide, and there is a
Ah,
reason for
okay.
that. So when the ARM came out, so the Cortex-M family was supposed to compete in a device in an area where it was majorly dominated by 8-bit and 16-bit microcontrollers.
I see. I see.
And with 8-bit means you can do the same move instruction within 8 bits, what you will do in 32-bit. That means now you need 4 times memory just to tell that you want to move memory from one place to another. So that means
Fair,
you
fair,
need four
fair.
times the memory to store them. And that's what we call code
Hmm.
density. So code density was very poor.
Right.
And that
In
means you
32
need
bits.
much bigger flashes now to support to support ARM for the same program. So in order to tackle that,
Right.
ARM came up with something
Hmm.
what they call thumb instructions. So ARM initially
Right.
started having two instruction sets. One was called thumb and one was called ARM instruction set.
Right. So ARM instruction set was the 32-bit, and
Was
the
the
thumb
original
was the
32-bit instruction set. Thumb is the one which is a code density optimized thumb instruction, but it is not that
right.
powerful because you can see, right, just because now you have lesser bits to encode the information, that means some operations are not possible in thumb, but they were in
Correct.
ARM.
Or you right, right. Your variety of instructions are limited, and the
Yes,
number of registers you can access within the CPU, those are
exactly.
all limited.
So
Okay.
in thumb, you cannot access the higher register address space, which is R7 to R12. So in order to
Uh-huh.
skip this confusion, ARM came up with something called thumb 2,
Right.
which is basically a mix of both 16 and 32-bit instructions.
Right.
And instead of user, so earlier user has to manage switching from thumb instruction set to ARM instruction sets. Now it
Mhm.
automatically happens with thumb 2
I
in
see.
hardware.
So the hardware automatically detects if an instruction is 16-bit or
Yes.
32-bit, and then accordingly
Accordingly
executes
takes
it.
care.
Fair.
So what does this
Right.
mean for our pipelines? So if
Mm-hmm.
it was a 32-bit instruction, it is fetch, decode, execute, like a very traditional pipeline what you see in images.
Correct.
But
Correct.
in
Correct.
16-bit, your fetch logic is still 32-bit. That means
Mm.
you are fetching two instructions at a time, but you can
Understood.
execute only one.
Right.
So the pipeline becomes a bit different in Cortex M4,
Mhm.
where you have an empty space between fetch and decode for the second instruction because the fetch has already happened in the previous stage
I
itself.
see. Understood. Understood.
And this is where Cortex M7 takes benefit of it, where Cortex M7 has dual decode and dual execute pipelines.
I see.
That means it can decode and execute two instructions at a time, and that's what we call a superscalar architecture,
Correct.
right?
Correct. I was going to
So
mention
there it can pair. So it's like two pipelines running
that.
parallelly.
Right. So it is going to kind of fetch,
Two fetch, two decode
decode in parallel.
in
So
parallel,
there are
and two execute.
effectively, two units which are doing the
Yes.
execution. Okay. That makes the whole
Yeah.
execution and memory fetches data related operation a lot more funny and complex.
Yeah.
But again, the programmer doesn't have to deal with that. It's all hidden from the programmer.
Programmer doesn't have to
It's
deal with
just
it.
some internal,
So
magic.
yeah. So the aim of this is to, so whenever people start reading about CPUs, they just assume when it is 32-bit CPUs, that means everything is
Yeah.
32-bit in
Yeah.
there. Well, that's not actually true all the time.
Well, the 32-bit, the bit of the CPU usually refers to the register within the CPU, the data that it can operate on, the
Yes.
number of bits it
Yes.
can operate on. So a 32-bit machine can actually have 16-bit instructions. It's just that the data it operates on
Yes.
will be 32 or
Exactly.
less than 32, but at max 32. Yeah.
Yes.
Okay. Cool. So moving
Okay.
on to next slide. I see. Nice.
Okay. So when we talk about Cortex M, so whenever we talk about any risk-based processors will have something called a general purpose registers.
Right.
And we read it in the previous lecture, right? Why is it
Yeah.
so? Because the risk architectures don't want to complex
Hmm.
things, so they want to expose it to the minimal possible operation that you can do.
Right.
So even CISC may have these registers, but they may not be exposing those registers out.
Fair.
So here you are, and that's why we call it's a load store architecture. That means if you want CPU to process anything, it should be available in one of these general purpose
Right.
registers. So ARM Cortex M devices have around 50, they call it 15 registers, out of which only 12 are for general
Mm-hmm.
purpose. And rest three registers have a very specific meaning. That means they are not available to public for storing anything they want.
Right. I'm wondering if I made an error here. So R0 through R11 are available, and then R12, R30. Oh, never mind. I think I wrote it correct. So R0 to
Yeah.
R12 are available for the programmer to consume, but these are like 13
Yes.
registers, not 12. Yeah.
13
And
registers.
then R13, R14, and R15 are for special purpose. R15 being
Yes.
the program counter, R14 being the link
Yes.
register, and R13 being the
Yes.
stack pointer. Well,
Stack
people
pointer.
can also, not people, but the programmer can also manipulate these, right? It's just that you can't use it
Yes.
for computation, like add,
So
subtract.
that means the purpose of this is that means that programmer doesn't have exclusive
Right,
access to this. CPU can on the behind
right,
modify them.
right.
While for R0 to R12, it is all controlled by the
Understood.
programmers.
Yes, yes. So see,
ARM will not manipulate
understood. So
them.
the CPU kind of, automatically can go and modify these for its own
Yes,
purposes. Right. Yeah.
purposes.
Fair.
So, and in ARM, and we talked about it, right? So ARM has two execution modes, which is thread and
Hmm.
handler. So you want to separate the stack pointers for this. You want kernel to have its own stack pointer, and you want user space to have its own stack
Right.
pointer. So that's why ARM has two stack pointers in it, which they call main stack pointer and a process stack
Right.
pointer.
And-
As you can see, process stack pointer means where the processes are executing. That means the user
Yeah.
space.
So this is the
So PSP is the one for thread
Mm.
mode, and MSP is the one for
Right.
handler mode.
And from what I recall, actually the handler mode can also use PSP if it wants to, right? But the
Yes.
thread mode always will use PSP.
So it's actually like this. You can segregate and control which stack pointer to use. So control register
Mm-hmm.
controls it,
Mm-hmm.
whether you keep on using main stack pointer or you switch
Oh,
to
fair,
a
fair,
process
fair,
stack
fair.
pointer. So it is up to kernel. So kernel, while switching back to user space, has to clear that bit in control
True.
register,
But
telling the CPU to stop using MSP.
okay. Um, okay.
So if you're not clearing that bit, the thread mode can keep on using main stack pointer. You never have to set up process stack pointer.
Okay. So I think my understanding is a little flawed here then. What I understand is handler mode could use both, but the thread mode can't. Okay, what happens if here's the situation. What happens, let's say the thread mode is using main stack pointer and it runs into a stack overflow. Then there
So here's the thing. So thread doesn't. So in a space where it is thread and handler mode, kernel and user space, the control register is not accessible to thread
yes,
mode.
yes.
So it is kernel's responsibility to make sure that thread always uses process stack pointer and not the
I
main
see.
stack
I
pointer.
understand, but let's say you're saying that if the kernel did not switch to the process PSP, then the thread
Yes.
mode
So
can use.
then the stack R13 will still keep pointing to MSP.
Okay, that is interesting. That is very interesting.
So that bit is used to define. So ARM for complete its complete processing doesn't refer to MSP or PSP. It refers to R13 register, which is the
That is
stack
true.
pointer.
That is true.
The control bits. So the control bit controls that
Hmm.
R stack point that R13 is pointing whether to MSP or
I see.
PSP. So unless kernel
Right.
clears that, R stack pointer will keep pointing to MSP. And that's why
Huh.
if you don't have this whole kernel user space concept, you can run your complete system without ever setting
Hmm.
PSP, irrespective whether it's thread mode or handler mode.
Fair.
You always set up only MSP.
Hmm. Fair, fair. I think I understand that. So just to summarize it for our viewers, the idea is that the SP will have one of the values of these two shadow registers, so to speak, right? By default, it will be
Yes.
MSP because it starts off in the handler mode, the reset handler. And if when switching to thread mode, this is not changed to PSP, it only means that the value from PSP is not copied to R13. The CPU will
Yes.
continue to use R13. Whenever we change using this control register, the stack pointer, shadow register, whatever is the value in them will get copied to R13. That's the idea. But the CPU
Yes.
continues to use
Yes.
only R13. Okay, fair, fair, fair,
Yes.
fair. Yeah, this was something that I did not know. Yeah. Okay, cool. Let's move on.
Right. Then we have something called program status register, which
Mhm.
basically records what is the state of the CPU at a certain point of time.
Mhm.
What was the state of the ALU? What was the state of the interrupt registers? What it was trying to execute and everything.
Mhm.
So we will go into much details on this in the next
All
video.
right. So
Uh,
this is
so
where it is recording status like was a zero generated, was a negative number generated, was
yeah,
there an overflow, and so on and so forth. Okay, fair.
yeah. So I would just like to bring a very interesting fact over here.
Mm-hmm.
So when we talk about zero, right, it's a very useful constraint,
Yes.
specifically in all our instructions. So you will find multiple instructions like branch and jump if
If not
not equal
zero,
to
yes.
zero, compare if not equal to
Yes.
zero. So they usually refer to this
Hmm.
bit. whether this bit is set
Right.
or not.
Hmm.
But nobody thinks how that bit was set to 1.
Hmm.
So usually CPUs on a back will always compare it to a register that they have not made public, which
Uh-huh.
contains only value
Right.
0, and set this value to
Right.
0. So a lot of CPUs were doing it, while a lot of computer architects made a decision that this is a very useful concept and made it a public register as well. So if you go to MIPS,
Yes.
etc., the 0 register is actually 0. You cannot store anything
Right.
else in
That's the
it.
case in risc-v also, and I think ARM-A.
risc-v as
Yeah.
well, and that is the case with the 𝘂𝗚64, not with ARM-A,
Oh, yeah, yeah, yeah.
𝘂𝗚64.
True, true, true. I think V8.
So ARM was going in the opposite direction where they were not doing it, but they realized it that it's
Right.
very useful, and they like made it a
Right.
public register in
So,
𝘂𝗚64
right,
as well.
when we say 𝘂𝗚64, it's like the ARM processors, A-class CPUs that support 64-bit. Right.
Yes.
Okay. Perfect.
Yeah.
So,
Okay. And
go ahead.
now the second, so we will cover the status registers in
Hmm.
detail. The second group of registers that you have over there is exception related registers. Basically, how we since Cortex-M has internal
Mm-hmm.
NVIC, and so they are separate NVIC registers as well to configure NVIC. But it has some internal registers to define different things. What instructions can interrupt me, what instructions cannot
Right.
interrupt me, what should be the base
Right.
priority, whether Cortex-M CPU wants to get interrupted or
Hmm.
not as
Hmm.
well. So that is what we call a prime mask, fault mask, and base
Hmm.
priority.
Okay, you're
So
talking about
using
the.
this, you
Right.
can control the complete interrupt behavior on the Cortex-M
Let's pause
devices.
a second, because when you were talking about the exception related registers, I mean, these are the ones, yes, but these are like relating to
Yes,
configuration of the exceptions, right? The priority
yes,
mask, the fault mask, and the base priority. But I was kind of hovering on these, and I would like to speak to these.
okay,
So the whenever an interrupt happens, which interrupt happened, that number gets populated here in the IPSR, which is called the interrupt program status
yes.
register. And I don't recall what the execution program status register holds. I think
So
it
yes,
holds that uh, if
yes.
then
So
else
if we go to the
execution
next
something.
next page,
I see.
if we go to the next slide,
Yeah.
so we'll cover the program status register. I guess we can skip this one and we'll come back to this one. Let's go to next one.
Okay.
Again, next one.
Right.
Yeah. So this is
Next
the program status register.
oh, right.
Yeah. So the interrupt status register is the ISR number. So whenever an interrupt gets active, the ISR number is stored over there.
Mm-hmm.
The execution program status register, it contains something what's called if then and if interruptible instructions. So
Correct.
basically ARM supports multiple load and multiple store instructions, where
Yes.
you can load a continuous memory
Hmm.
directly into multiple register at one go,
Right.
and you can also store, and so you can use all the R0 to R7
Right.
registers
Right.
and load
Right.
like 128 instructions in one go, in one instruction, not one
Uh-huh.
go.
In one instruction.
So you can load like 128 bit of memory into 4 registers
Mm.
in one instructions. It will happen in multiple cycles.
Right. And then
So that's what ARM calls a interruptible instruction,
correct. And then while
because
that is happening, I suppose, is it this that gets set? Well,
yes.
actually,
So this gets set and the 10 to 15 tells which up to how much it has done
okay, okay,
completed.
okay. This is like the progress.
This is the progress, and that is the
Right.
flags.
Understood.
That is the flag that I was executing something like if interruptible instruction or if then
Right. And
instruction.
then this is the thumb bit, which
This is the
which
thumb
I
bit
think is
that tells whether ARM is executing a thumb instruction or a ARM
right. And I
instruction.
suppose in Cortex-M's case, it defaults to 1.
Yes.
Unless I think 1 denotes thumb 2.
It is dynamically handled by
Okay.
the
Fair,
CPU.
fair, fair. Fair.
We don't
Mm.
have to control it. That's the point of
Right.
thumb 2.
And this is depending on whether it is executing that 32-bit instruction or 16-bit. Right. Okay,
Yes.
perfect. And then these were the APSR bits. Now,
Completions.
right,
APSR,
right.
application
What I
plug.
want to call out is, although this register is called the PSR, it is mixture of these three registers here.
Yes.
And so if we were to read APSR, we would only read these many bits, right? On all of these would be zero.
Yes.
Similarly, if we were reading
Yes.
the IPSR, we would read, those the intermediate bits, the middle bits. And if we were reading the sorry, I mixed it up. If we were reading the IPSR, we would read the lower 10 bits, which are these, right? And
Yes.
then if we are reading the EPSR, so we'll read those middle bits, and all of them
Intermediate one.
combined is PSR. So these are like four different registers,
Yes.
right? Okay,
Yes.
perfect. And then you talked about these. Okay, to speak to the control. Speak what the control register does. So I think it only has two bits.
We don't need to go into much details. I guess we already looked into one of the use cases of control register, which is where it controls which stack pointer the SPR 13 points, so whether it is MSP or
Right.
PSP.
Well,
We'll go into much
yeah.
details because the thing is, you don't manipulate. You should not manipulate control
Right.
register quite
Right.
often.
And,
Uh, so that is more of an advanced use case. In a normal use case, people will not touch around it, and I don't want to take those advanced use case over
sure.
here. We'll cover that in a complete Cortex-M4 in-depth
Fair.
things where we cover each and every portion in
Sure, sure.
details.
So I think what people should take away from this slide is GPRs are 15 in number. Well, actually 0 to 15, so
Yes,
16 in number, out of which 13 are available for the programmer to manipulate. 3 plus 3, which the CPU can also modify, which is SP, LR, and program counter. Perfect. Okay, so
yes.
then moving on to the stack frame. What are we talking about here?
So the reason for this slide is so why do designers reserve a register for stack pointer?
Mm-hmm. Mm-hmm.
Like, what is the purpose of stack pointer over here?
Right.
And why do we so the stack is a very useful data structure for a program execution.
Mm-hmm.
And so rather than keeping track it in software, so CPU designers keep it a register to keep track of the stack and the execution flow.
Right. Right.
So stack actually stays in the memory itself. There is no internal memory to CPU where it stores the execution. It uses the public
Right.
memory, SRAM or
Mm-hmm.
something, to store over
Right.
there. So whenever we talk about any program, and this is not only related to C, this is related to any programming language out
Mm.
there, because it all relies on the concept of local and
Variable.
global.
Yeah. Yeah.
So whenever you have something like a local
Variable. Local
view,
view. Okay. Context.
local
Yes.
context, local
Yeah.
context. What local context and local scope means is you don't only have access to the memory that is there in that execution flow between those programming
Hmm.
braces. And how programming languages emulate that is by putting them into something like
Hmm.
stack.
Correct. Stack frame essentially. So every
So
context
stack frame.
gets its own stack frame, some region on the stack where the
Yes.
local variables are available. And
Local variables different things are over there. And so each of the function has it, and when the function goes out of scope,
that stack frame
the
is
stack
destroyed.
is nobody frees up that
Right. Right.
memory. What CPU cleverly does is just manipulates the stack pointer to go
Right. So
down
the stack pointer will come.
to the previous stack pointer, and that's how the jumps
Right.
etc. work.
Right. So I think the key that we wanted to give away from this slide was why a stack pointer is required, and the answer to that is to
Yes.
preserve the local context, right? So in this
Yeah.
case, I suppose what you wanted to, let me just get rid of a lot of scribbling here. So in this, what you were wanting to highlight is, so the main function, when it calls the add function, so main stack frame is available here, and when it calls the add function, the B and A.
A new stack frame is added for
Mm,
the add function, and the stack pointer is moved
right,
up.
it's moved up, which is here, and all the local variables are available here. And while it returns the C value, which is available here, C value, okay, there we will not go into the ABI, but this C value will get
Yes.
put into like one of the CPU registers while this frame is
Yeah.
while the stack pointer gets reset back to the frame of
Yes.
main, so to speak, or the context of
Yeah.
main. Okay, perfect.
Yeah.
Hopefully we didn't confuse people. If we have, I think we'll just get back to it uh, later again, and things will be much more clear. Okay, perfect. So
Yeah.
we talked about this already, and I think then we are at the end of session for today. Do we
Yep.
want to
Yep.
maybe just do a quick demo on showing the internal registers, just so that people are convinced that it actually is a thing?
Uh, Maybe we can start a debug session and show all those
Right.
registers, but how those value changes, let's move it to a next
Sure,
chapter where
sure.
we focus completely on.
Perfect. So let me do
Yeah.
this. Let me, go to the code space that I had created. So I think the source code here is not important. What we want to show is on an emulator that an M4 CPU would have all of these registers that we talked about. So let's wait for the code spaces to fire up. Yeah, I think activating. Right. So what I'm going to do here is first off, get two terminals and just okay. How do I? Can I move the terminal here? Nope. Okay, let me create one more and then move that here. Okay, and so this is some repository, ESH repository, of which we'll add the link in description. So I'll just go to the examples, then emulation based, and then V7, I suppose,
Yes.
V7M
M32.
M32, right? And then let me also go into CD examples, emulation, V7M32. Get rid of this. Let me build our example. Aha, okay. What happened here? Okay, we don't have the
GCC not
toolchain.
found.
I'll need to install that. Yeah, I think we are caught by surprise here. Yeah, this is going to take a while. All right, almost there. Okay, fair. Cool. So I think, okay, emulation V7M32. Okay, make, yep, all good. Make debug, nice.
Maybe.
And we don't need this. And then we say make GDB, nice. So these are
Yep.
then the registers that we were talking about. The APSR is marked as CPSR. I think, what does CPSR stand for?
Yeah.
Program status register, I suppose.
CPU program status
Okay.
register. So basically, PSR has been marked as
Right.
CPSR.
Oh, it's just the P. Oh, okay. Obviously, yes. The PSR, not the APSR. Yeah. It has the full information. So the
Yes.
bottom,
So this is the complete PSR.
right. Nice. Okay. And I think we can just let it continue. Uh, Pretty much our, what we wanted to demo is done. And then with that,
Yes.
we can, maybe close the call for today. And in the next one, we can dive into the
Yes.
exception model, I suppose. Yeah. Perfect. So, those
Yes.
who have still hung around, thank you for, being around, and catch you guys next time. Bye bye.